Right, welcome. Thanks for coming. Today, we're going to be looking at how to build testable, highly performant, event-driven applications. I'd like to introduce my co-presenter, Chris Hewitt, who's one of the founders of Redify. I've known Chris now for about 14 years. In fact, Chris gave me my first job here in Australia, and my second one. And now, Chris has been working in IT and working in the finance industry since the 1970s. And now he's joined us.
Okay, thanks, Martin. Martin was actually Redify's first principal consultant, also one of the first Microsoft architecture MVPs, and he was the author of Microsoft's Industrial Strength.NET courseware. Okay.
Yeah. Right, what are we going to cover today? We're going to start with our project and the requirements behind that. We'll look at push models versus pull models for building event-driven systems and why we chose to go with a push-based model. We'll then have a look at what I like to call temporal design patterns and how you can build them using reactive extensions. We'll then look at virtual time, or how you can virtualize time out of your application and make your application actually testable. At the end, we will give you some guidance in terms of whether it's worth your time wrapping your head around reactive extensions, because it's pretty mind-twisty. And we'll also take some questions and answers at the end.
Okay, thank you. So this is our project. What we're doing is building algorithmic trading engines for the stock market. So events occur on whatever the target market is at up to 10,000 events a second. And what we have to do is react to those events and then with about a 4 to 5 millisecond latency, make a decision and send buy or sell orders to the market. Yeah, that's pretty much all I got there. Oh, that's pretty cool, right? So, you have to have all these good things. So it has to be fast correct. So fast because, we have that low latency requirement. Lots of things happen. We have to be fast. Correct because there's real money riding on this. We can't afford to make mistakes. Customizable because we have to be able to slot in different modules. So it's a modular system, and we need to be able to drop in new and different and alternate modules at any time. And robust because, when you're halfway through the trading day and you've got a whole lot of positions outstanding, you don't want it to fall over and leave you in the lurch, and then all you've got left is an emergency exit strategy or something like that. I worked for a little while for a large investment bank, looking at an application, an online trading application, which basically was looking at a message bus and peeking from a message bus, getting the information off, and then making asynchronous tasks and sending it off to different parts of the application. About 10,000 lines of procedural code. And amongst the problems that had, which were quite a few, was that it fell over at least once a day per workstation because of concurrency issues. And it was also very slow and missed messages and things. So I guess it wasn't fast, correct, robust, or it wasn't actually customizable either. Okay. So, we have to decide how to build this application. So it's going to be a modular application. So we have a module that accepts inputs from the market at the beginning, decision, they're pretty self-explanatory. Now, one approach, and I guess we both used to be SOA guys a while back, right? If we were wearing the SOA guy hat, the market processor would, take the information from the feed. It's just coming over TCP or something, and let's say, and put it onto something like a queue. So the process up there might take it and put it onto, say, a concurrent queue or something. You'd use that these days. Or multiple queues, depending on what the messages were. And then there would be threads of control in each of the modules that would pull the information off the queues and use it and then pass it on. And that could be relatively fast. Okay, you could actually make that reasonably fast, and it would actually be easier to understand in a way than what we ended up with. But there are a number of problems with that. Because there are independent threads of execution in each of these modules, the timing is a bit difficult, right? So each module controls its own destiny, is in control of its own destiny, and will pull the things it wants and push the things it wants onto the next queue. It also means that it can't be repeatable because of context switching and stuff. You can put the same feed into this imaginary queue-based version of the system, and in 2 runs, you will get slightly different answers, right? Which is okay unless you're trying to simulate things or audit things or find out why something happened. So really, we need this to be repeatable. We need to say, if you get this flow of inputs at this precise timing, we want to see exactly the same outputs out every time we run this through. Because we have to also run it in simulation, right? We're not just going to go, oh, I think that's a good idea. Let's connect it to a bank account and turn it on, right? We're going to test the bejesus out of it, if I can use that expression. And to do that, we have to run it in simulation, and the simulations have to always work the same way. So, that's a problem that we're addressing. So anyway, oops, we're going to go there. Okay, yeah. What we're going to do now is talk about. So really, the queue-based model that we're talking about is like SOA, and what we're really going to do is the pull model we're talking about is like enumerable, but what we're actually going to do is use a push model, which is observable. Okay, so now we're going to demonstrate. Okay, there will be beach balls, all right? We're going to demonstrate the difference between enumerable, observable with beach balls. Okay, so Martin is an enumerable.
Hi, guys.
I'm going to call get enumerator on. Okay, and now move next. This is the easy part, by the way.
Yep.
Move next.
Yep.
Move next. Small problem, there are too many enumerables. But anyway, let's imagine there are no more beach balls left. Move next.
Yeah.
Dispose, all right? So that's how enumerables work with beach balls, okay? We need to put it back on again. And it's a matter of where control is. So with enumerables, you notice that all the arrows go in the same direction. The consumer controls the interaction between itself and the enumerable. So the consumer gets the enumerator. The consumer does the move next. The consumer decides when to dispose. That's pretty much all we want to say about that. You know what an enumerable is, right? Now the hard part. Okay, take these beach balls back. Never work with children, animals, or beach balls. Okay, so now Martin is an observable.
Yes. Oh.
Subscribe.
Okay. On next.
When I subscribe, I tell the observable that I'm interested in beach balls.
On next.
But the observable decides when beach balls arrive.
On next. Uncompleted.
And the observable also tells me when there are no more beach balls. Now, if an observable completes, I don't have to dispose it, which is an interesting feature of observables. Now, the thing to notice about this is, next slide. Who's got the clicker? Over there. It's here. Oh, you can click from there. Right. The thing to notice about the observable diagram is that control rests both with the observer and the observable. So the observer decides when it wants to subscribe to the observable.
And then the observable decides when it wants to actually send messages out to the observer.
And the observer can decide when it's no longer interested in messages from the observable.
And the observable can at any point say, I'm finished, and give notification that it has completed its job.
Okay. So what we want to note about this is that the that the arrows go in both directions, that control rests with both sides. Right. Okay. Is there anything else we need to notice about that? No? We could hand out some free beach balls. All right. Thanks.
We'll also be giving them out some quizzes later on in the session.
So we decided to use Reactive to implement this application. Now, okay, advantages that we got from this. Let's say that now messages come in, like these enormous number of messages are coming in all the time through the market data processor. Basically, the thread of execution that comes with the message we control this, right? May run all the way through to the issuing of an order through the trade gateway. Or we can control the concurrency. Basically, what these boxes are representing is that these are the modules in the system, and there may be more or less modules in reality. Just thought I'd say that. And these little thingies here represent just observables. So on the modules that they're coming from, they're observable properties, and on the modules they're going to, they're probably passed into a constructor. So we'll just take the properties of some other module and put it into the constructor of this one. Okay, so what's going to happen is that the message comes in on a thread, and the thread execution can just go through. We can decide what the concurrency is. We can make it go. We can make it go into multiple threads in the decision maker if we want, or not, depending on how we want to do that. Now, advantages of this, well, one of the big advantages is that the interfaces between all these modules are just iObservable, and iObservable is a very simple interface. So that means it's easy for us to swap in different modules to do different things. Am I going to? That'll do. Okay. All right, let's move on. Another advantage that we get from using observables is that we've got to put this thing, we've got to make this thing work and test it and simulate it, but when we really put it out there and connect it up to real money, it has to run on a box a long way away from us somewhere. Not really in Azure, but even though it's a little cloudy thing, but it has to run somewhere close to the target exchange. So we're not in direct control of that. But what we can do, and one of the problems that you have with Azure, actually it's got to do with Azure, right? One of the problems you have with Azure is that there's all these processes running up there in various places, and how do we get really deep, because we want to know exactly what this thing is doing. We want to know blow by blow that when the price of that changed by a slight amount, for a few seconds when we did something, why did we do that? So we need to really know everything. What we can do is we can take these observable streams that are going between the modules, and we can publish them out over WCF, over the wire, and we can monitor them, or we can record them for auditing purposes in other places, which is also something you can do if with some other application running in Azure that used observables to do inter-module communication. You could do that too. And what we've also done is we've made the state of each of the modules observable so that it sends an on next when its state changes, and we can also monitor that remotely over WCF as well. So that's actually a very important facet of the implementation, and a big benefit that we got from using RX. Okay. All right. And
Okay.
now I'm going to relax mostly.
So now we've got a little game. So if those people who've got devices can go to m.ozalgo.com, with the laptops, phones, even Windows phones will work. And it's actually optimized for landscape on the device. If you go in there, just put in your initials, and what we'll do is we're going to play a trading game where everyone can buy and sell shares in 3 prime stocks. Now, there will be headlines which will be appearing on your devices, as well as real-time. Oops. Okay. As well as real-time prices. Now, these headlines may indicate the potential direction of the prices. So those who've got a keen eye should be able to profit greatly watching these headlines. Okay. So if everyone goes there. And what I'm going to do is bring up the dashboard. When you sign in with your initials, we'll see whoever wins. And the winner will get this fantastic prize, which is a magnetic construction kit, within which you can actually build your own marble diagrams. And I'll explain what marble diagrams are later in the session, so it doesn't mean much to most people. But you'll be able to build your own magnetic marble diagrams. Okay. Okay, all right. So I'll just explain the UI. Buy and sell, see buying and sell of shares. If it comes up with a little number, that means that your order is in the market but hasn't been matched. It's actually a closed system, so it's only the people in this room buying and selling against each other. Okay, all right, let's see if it, see how it goes. It depends a lot on the network connectivity that we have. So, okay, got a few. Okay, so you can see we've got some winners. We've got so far CB is the leading winner. We've got the headlines going up there. As you can see, the Microsoft shares just rose pretty sharply on the news of the Xbox tablet. Sorry, is that a? Am I allowed to talk about that? Not sure. So whoever MN is doing pretty well. Who's MN? Yep. So I don't know what the network's like. Is it starting to come through okay for everyone? Oh, sorry, I don't know if that one was meant to be in there. Oh yeah, that's better. So let's run this for a couple of minutes. So this is an example of actually using RX in lots of different places. Again, I haven't actually said what RX is, but we will get to that. We're using RX here for both the UI in the device. There's actually a JavaScript version of RX. So we're using that for long polling and doing analytics on the device to produce spark lines. We're using it in the matching engine to match the streams of orders and prices coming in together. We're using this in this controlling console, for obviously the prices and the news feeds coming in and doing some calculations in terms of profits going on. So there are lots of different places where we can add little bits of processing where we've got real-time information coming in and we want to make it work. Okay, so we'll just give it another 30 seconds, although we've still got MN's doing pretty well. You can actually buy and sell. You can actually go short in this as well. You can go negative holdings. So, it looks, I think it looks pretty clear that we have a winner here. Did
you say the bad thing about magnets?
Oh, yeah, good point. With the magnets, for the winner who does win, don't put it in your bag next to your computer. I am not liable. Oh, sorry, legal. These headlines no way represent the opinions of myself or my company or other stuff like that. Please don't sue me. Okay. Okay, I think we have a winner. Oh, actually, oh, we don't. Oh. Wait. Okay. Okay, there we are. That's I think we'll claim MN as the winner in this one. Okay. Yeah. Okay. Thank you. Right. Sorry, for those of you who didn't have devices, that's kind of what it looks like. I said the real-time graphs and so on all works on the devices. Unfortunately, it doesn't work on Windows Phone 7. It does work on Mango. But that's not my fault. Okay. It does work on Mango. Okay. Right, Chris, do you want to hand out do the honors? And I'll swap over. Okay. That was all running in Azure as well. with RX streams flying around and using Azure queues. For those who are interested, I'll be doing a demo, hands-on demos tomorrow at midday and at, I think, 1:30. Actually, I'll just get, if Nigel can just check that. Okay.
You're going to be wanting a slide deck.
Okay. That's a bit of light entertainment, but it does show where you can use RX in various different places in your project. Okay, well, why should you care about this? What's in it for you? Above this green line, it's a bit of a complicated slide, I'm afraid. Above this green line are asynchronous technologies or asynchronous platforms. Now, we're not talking about concurrency here. There's lots of concurrency tools all over the place. This is about asynchronicity, being able to program your program flow asynchronously. What we have here is we've got going from native close to the bare metal to very abstract. We have stateful systems going through to functional or removing state as much as possible, or immutable state. A lot of you will have heard about the await keyword that's coming in. It allows you to do procedural asynchronous programming. RX is the asynchronous dual or mirror of LINQ. So LINQ allows you to do declarative querying over synchronous collections, or synchronous declarative querying over collections. RX allows you to do asynchronous declarative querying over asynchronous collections. And this is where the interesting problems are, right, above the green line. That's where everything's going. So what is RX? RX is a library for composing asynchronous and event-based programs using observable sequences. What the heck does that mean? Observable sequences can be thought of. Everyone's used to a list of some type as a collection. You can query it, and you can go through all the items, and it has a well-defined beginning and an end. An observable sequence can be thought of as a collection of future events which may never finish. Okay. And that's quite a hard concept to think about. But you're passing around in your program these collections of events which may occur at some point or may not occur, and the collection may be completely open or it may be closed. We're going to take these collections of future events, and we're then going to build a whole set of operators that transform from one collection of future events to another collection of future events. And that's what RX does. Let's go back in time. Let's go back about 5 years ago, in fact. This slide. At the time, there was this LINQ project, Vision. And the vision was to produce a language which had a set of standard operators, and then there were providers over underlying data sources which those operators could work against. What is interesting is that each of the providers for the different data sources was allowed to change the semantics of what that language meant. So when you said a where clause, you tell me what that actually meant. When you said, for example, concat, well, SQL turns that into a union all. Most people would be used to standard query operators over objects, over lists and collections. RX is standard query operators over these collections of future events. So it provides all the standard query operators and adds more operators in turn. Another way of thinking about these operators, so this is quite mind-twisty, trying to get your head around these collections of future events. Another way of thinking about operators is if you were to build a cheese factory. Right? Of course, everyone wants to build a cheese factory. Right. Like this. Here is a cheese factory. And one way you can think of these operators is as conveyor belts. Each operator, something gets dropped onto it, the operator does some work with it, and then the item falls off the end of the conveyor belt to the next one. Right? The next conveyor belt can go along to the next one. You can think of the observable as looking at one end of the conveyor belt. It's looking at it, and every so often, a block of cheese will be thrown at you from the conveyor belt. Okay? And that's the observing of it. But the composition is putting all these conveyor belts together into a chain. And so a chain of linked operators can be thought of very similarly as a chain of conveyor belts. And in fact, in here you've got merging and all kinds of nice operators happening. So if that helps to, it may help to visualize what the operators mean. Okay, from cheese to abstraction. This is a quiz, and we have a beach ball to give out for this one. This is a bit of link. In an enumerable world, if we had A was a list of numbers, and B was a list of numbers, we ran this query with a to list at the end. Say we had 5 numbers in A and 5 numbers in B. How many numbers are we going to get out at the end? 25. Oh, yep. Sorry. Yep. Okay. 25. Well, so I'll give one for that one. That's kind of the slightly easier one. Sorry. There. Now the harder one. If A is an observable of numbers, and B is an observable of numbers, and we subscribe to this whole chain of linked stuff, how many, and each, A is going to fire out 5 events of numbers, and B is going to fire out 5 numbers. How many numbers do we expect to receive at the bottom?
5.
So we've got a 5, we've got 10s? 10. How many else have we got? Infinity, okay. I think my memory might blow up, but anyone else? 0. Okay. Anyone else?
0 and 25.
Bingo. The answer is, as all architect questions come out with, it depends. Yeah. So. Yeah. So the question is that dependent on the order in which things are added? Yes. Well, the order in which they fire. Yeah. So, for example, if B fires everything first, so it was a bit hard for me because I didn't actually explain what this means in English. Let me restate what this says in English to everyone. I'll do the list version first. For every item in A, call it X, and go and get every item from B, call it Y, and output X plus Y. That's the list version. The observable version is the following. Subscribe to A. Whenever we get an X, go and subscribe to B. Every time we get a Y from B, push out on next an X plus Y. So the ordering is important. If B fires out, so we start out subscribing to A. We're waiting for A to fire some numbers. B goes along and goes pop, 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 pop. Who cares? It's like a tree in the forest. Right? Fallen, but no one's hearing. No one's listening to it. And then we get A fires 1. We go, OK, let's subscribe to B. Great, we're subscribing to B. Wonderful. A fires another one. We subscribe to B. Okay? And at point, so A keeps on firing. So we've got 5 things coming from A. We've subscribed to B 5 times. But nothing's coming out of B. So we get 0. We get nothing. If, on the other hand, it's the other way around, all the A's fire first, and then the B's fire, each A, we subscribe to B, and then, so we've now subscribed to B 5 times, and then B fires, that comes out on each of those subscriptions. B fires, comes out on each of those subscriptions. B fires, each of the subscriptions. And we get 25 out at the end. So you can see we're going from 0 to 25. So we've just added an extra dimension to our programming, which can be good and can be bad.
Does that queue up the A's until the B's fire, basically?
No. No, and that's the point. That's exactly it. Because what's happening is when things occur becomes important. It's not just what things are in the collection, but when those events fire that becomes important. So it's not just, I actually wasn't telling the whole truth before. I said before it was a collection of future events. It's not just that. It's a collection of future events and when those events occur. Right? Because that is actually almost part of the data. Right? When the events occur affects what the outcome is going to be. And so you've got to think about the when of this as well as the what. I didn't warn people at the beginning. It's quite mind-twisted, did I? Sorry. The advantage of this is it starts to allow you to solve problems that were previously intractable. Because you have the whens, and you can then start creating operators and patterns to say how you're going to deal with different circumstances. How are you going to deal with A happening first before B, or vice versa? And you can start to specify that. And you can start to declaratively specify that. Okay. What I want to do now is give you a little nibble at the RX cheese factory and give you a bit of a taste for the language. So I'm not going to go through the whole lot. I just want to give you enough, hopefully, that you'll get an idea of the kind of scope of what sort of problems it's trying to solve. And the way we're going to start is with the marble diagram. So here is a select statement. And what we have, A is an observable, select is an operator, and the whole of that A.select is an observable. We can observe that and get the results of it. What these lines represent, this line here represents the observable A, events firing on it. This line down here represents events coming out the end of the select operator, the whole observable. Left to right represents time. So we're starting off here. Time's ticking away, time's ticking away, time's ticking away. An event fires off A. The select operator works on it, adds 1 to the number, and then fires out a 2. Time ticks away a bit more. Another event fires on A. Select operator takes it, adds something to it, fires it out. Time ticks away, time ticks away, time ticks away. You know, you go off, the computer does whatever it's doing. And then another event fires on A, select does its work, and outputs a marble at the bottom. Any questions about what that's doing? So it's kind of the way that we tend to describe RX operators, because we have this time dimension involved. Okay. Start getting interesting. We've talked about these observable sequences. One of the things that we like to do is combine sequences. For example, you may have a stream of data from over here, a stream of data from over here, and you want to combine them together in some fashion. RX provides a set of operators to help you do that. One is combine latest. Now, one of the cases where we use this in our project is to do valuations. We have a stream of all the units holdings we have, right? How many shares we're holding, going up and down. So in this case, we get 1 share, we have 2 shares, we have 3 shares. The other stream we have are prices. So we have a price for stock, which is $1. It's gone to $1, goes up to $2, goes back down to $1. What we want to do is we want to have an event every time the value of our holding changes, which is the share price times the number of units we hold. And we only want to get an event then. We don't have to poll things. We don't have to do all this. We just want exactly when it happens, when one of those 2 streams changes, we want to get the price recomputed and output. So combine latest helps us to do this. So A, we get a price. Okay, well, we haven't got any holdings. Nothing happens. We get another price. nothing happens. We now have a holding. Combine latest logic is whenever something happens on this stream, get the latest value on the other stream, and do whatever is in this bit of functional code up here. In this case, multiply the two values together. So multiply together, get $2. With the next one, takes the latest value, multiplies together, $4. Next one, twice this time, so it takes this one and the latest value from over here, multiplies together, $2. Another one here, multiplies together, and $3. So this is quite a simple behavior that we're able to define how we're going to merge these streams together, these two bits of data, and get some results out. Okay. There's another type of combining operator that they provide, which is zip. This one's really useful if you've got, for example, buy orders and sell orders. What you want to do is you want to match up like a zipper. So this one match with that one. Next one, next. Right? Effectively, you're going to queue up typically one side until the next side comes in, and then you're going to match them up in together. For example, we get, say, a buy order in here, get another buy order. A sell order comes in, we're going to match these two together and output a single marble. This one comes in, take those two, join together, create a single marble. That one comes in, there's nothing on the other side. This one comes in, join them together, create a marble. So this is a different way of combining two sets of streams. And there's a whole series of different operators like that for combining streams. Okay. Now we start getting a bit more interesting with time. This operator takes the observable collection from the left-hand side and delays all the elements in it by a certain amount of time. So time's ticking away, one fires up here. We don't see this down here. We don't know that a one has fired. Time ticks away, two fires on A. We don't see that down here. Time ticks away. Now we've got a delay of this amount of time. Suddenly we see one. And then we see two. And then time ticking away, then we see three. So this is doing a delay. Now I've got a quiz coming up. I'm just going to use two of these operators. I'd like to see if anyone can guess what you would use this combination for. So it's quite a tricky one. Okay. I'm now combining, I've got a little extra there, but I'm basically combining those two operators together. So I'll explain what this says, and then ask if anyone can guess what you'd use this for. This one's actually quite a hard one to get. Okay. We're going to take the source events A. We're going to delay all those events by 3 seconds. That's going to create its own observable, which is the same ones but delayed by 3 seconds. We're then going to combine that with the original observable. So what is going to happen is something's going to fire on A. So you might get one thing fire, two things fire, and then a little bit later, they'll fire over in this bit up here. Now they're combined. I'll show that diagrammatically, and then I'll ask if people can guess what's going on. So time's ticking. First item comes through actually from over there. Doesn't have to come from over there. It can come from over here. Comes from A. Another item comes from A. Now the delayed item comes from the left-hand side of combine latest. Then the other delayed item. And then another one comes in from A. And then a delayed item. Okay, yep. We have
So you can see the price increasing or decreasing by 7
exactly. It's the deltas between, yep. It's a differential. It's a time-based differential over the same stream. So it's telling us at each point in time what the difference is between that value, the latest value we have at any point in time, compared to the latest value we had 3 seconds before. So it's effectively a rolling window. Okay? And for people who've built systems where they're trying to do rolling windows, they're actually pretty hard to get right with concurrency and all the other issues around trying to get events happening and not having extra events, and making sure that every time the window clips over, you do get an event exactly at the right time. Exactly when you get your 3 seconds over, it drops down, drops up, and so on. And that's it. That's how you do it. Right? That's how many characters over an observable. So for me, that's impressive. And it's just a small example of how you can start to build your own design patterns, your own temporal design patterns, using this language. It's really a set of building blocks to build algorithms for solving time-dependent or sequence-dependent operations. And the last bit of code, I know it's an architect's session, so I shouldn't be showing code. The last bit of code I'm going to show is the window operator. So we've talked about a rolling window. If you want to do hopping windows, which is where you chunk up time into hop, 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 and you work out some metric over that window. The window operator, funnily enough, does that for you. Takes a stream, and what it does is every period generates a new observable for that period, and then drops the marbles into that observable. So in this case, these get dropped down to here, that gets dropped down to there. Then the sum operator takes an observable, sums up the items on the observable. At the end of the observable, outputs a marble. So what we can start to do is combine these things together. The window generates the observables, the sum computes the observable, and the select outputs the value that we've got. That's how we can start to build really very powerful computation over these live real-time streams and do some very sophisticated processing over them. Oh, okay. Is there a blank? Oh, sorry. Right. That's all quite heavy. Now, when I was going through this and building the slide deck, it reminded me of a few years ago. I brought my wife and kids to Sydney. We were staying at the Maritime World Towers, and it was getting late, and the kids were getting hungry. The three of them, they're ravenous creatures. And so my wife sent me down to get sushi, because they all love sushi for some strange reason. And downstairs, there's a really nice sushi train restaurant. So for those who don't eat sushi, you go in there, you sit down, and you've got the sushi comes around on a little train going around, and you pick up the plates of sushi off the train, put them down, and then at the end of the meal, or you eat them, at the end of the meal, they come around, they tally up how much it's going to cost, and you pay. Well, as I was putting slides together, I thought, you know, that's actually an observable. It's actually an observable of sushi. Right? Because, no, hear me out. Because the person that's in control of the speed of the sushi is not me, but the chef. Now, in a normal restaurant, in other restaurants, you go in there, you sit down, the waiter comes to you, and you order something for the waiter, and then you wait, right, while they go and cook the food. And then they bring the food out. That's an enumerable model. Observable model is the sushi train. You sit there, the sushi comes along, you pick up the sushi, you eat the sushi. And then I was thinking, actually, not only is observable sushi, but I'm actually like a software agent. Right? My wife has programmed me with a set of instructions about how to go down to the sushi train and to collect sushi for the kids. So I thought I'd work out what my programming was in reactive terminology. Okay. So, first of all, right, sit down there, and first thing I'm going to do as these beautiful sushis going past is work out, I've got to only take the dishes which the kids are actually going to eat. Okay. Then I need to work out, as the dishes are coming off, how much it's going to cost me. So I've got to add up all the cost. Now, I can keep going until my wallet runs out, because I said they're ravenous creatures, so that can sometimes be an issue. I've got to take the sushi off the plate, put it into the thing, and then this one's actually a little bit more interesting. I've got to buffer it. Right, so I've got a bag, which I'm going to buffer into, but I've got a couple of behavioral rules. One is I've got 3 kids. They're pretty competitive. So if I went back to the apartment with just 2 plates of sushi, that would not be good. Right? Be lots of fighting. So I need to make sure I get at least 3 plates. On the other hand, this was getting late. And really, if I didn't deliver some sushi within 5 minutes, then I'd be in trouble. I can't win really either way. So I have to either, if a timeout happens, if it's at least 5 minutes, sorry, if 5 minutes happens, I've only got 2 plates, I'm going to take it. Or as soon as I've got 3 plates, then I can go and deliver it. So I'm buffering with time and count. And then I've got to go and deliver the sushi to the door. My wife will take the sushi on next. And then I'll go back to the sushi train and go and get some more sushi while the kids are enjoying themselves eating the lovely sushi. And then if the kids, so I keep doing that, keep repeating that, until if the kids have had enough, then my wife can call me up, and my wife can dispose me. And I stop getting sushi.
You could have completed.
Yeah. Okay. So as you can see, we can start to build these kind of design patterns with some of the operators that RX provides. And there's a whole different set of operators they provide, splitting, combining, time-dependent, and so on, which allows you to start building some very sophisticated models over your data and start building, as I said before, temporal design patterns. Time as an aspect. Who here has used some kind of aspect-oriented system or dependency injection system before? Have you got a show of hands? A few? Oh, maybe a third? Okay. One of the things that we're generally quite happy about doing is abstracting out of the core business logic functionalities such as going and getting configuration or doing logging or doing data access. I tend to abstract that out into data access layers or use dependency injection to get interfaces and then ask those interfaces to do the work for us. It's all fairly typical type behavior. What we see with RX is starting to abstract out control flow. What we do is we build our RX queries. We say, go get them Rex, and then the query will run and then return the results to us in its own sweet time, or as the results are coming through. The other thing we can abstract out is time. Often we have time embedded into our application. Timeouts, for example. Right? We're going to go to a website. If it doesn't return within a certain time, we're going to try and do something. More sophisticated, we can do the buffering type approach we talked about, or windows over time. What we can do with RX, we can start to abstract that out of our application. And they have a model using schedulers where a whole notion of time gets delegated to someone else. We say, what time is it? And they tell us. We say, have 3 minutes passed? Yes, it has. Now, the reason this be useful, there are a number of reasons why. First of all, testing. I've got my unit test. I did say at the beginning of the session, this is about also building testable event-driven applications. My unit test can actually feed time to the thing we're testing, feed a notion of time. For example, we may say in here, if we don't get any events for 3 minutes, then we need to do something, raise an alert, or do some kind of processing. If we're unit testing that, want to have to wait 3 minutes to test that behavior. Right, so we need to be able to supply some concept of time to the thing we're testing. And once we do that, we can supply time, we can provide an observable of events which go into it, and we can then monitor the observable events coming out. That combination allows us a great deal of fidelity in our tests. We can really test very fine aspects of how things come together. When you've got two events firing at exactly the same time, what happens? Or very close to the same time, what happens? So on. The other place it becomes very useful is in simulation. We can run, in the test model, the test provides the time. It says now is 10 o'clock, now is 10:01, so on. In simulation, the database provides the time. The data, in our case, we have information flowing from a virtual marketplace with a timestamp on it. We can use that timestamp to drive the whole clock of the application, which means we can run it very fast. We're not actually waiting for any kind of time to elapse. But we still get all the capabilities of timeouts and buffering and windowing. And the most important thing is it's all repeatable. It's all deterministic. We can make sure that the simulations, every time we run it, we get exactly the same results, even with all this kind of time-dependent behavior into the application. And it runs as fast as CPUs can go. We're not waiting for anything. We distribute it over lots and lots of machines. In the real world, we're still going to actually use virtual time, but that virtual time, the clock is going to be run by the market. The market is telling us what the time is, and that's what's driving our processing. This works through, as I said before, schedulers. So what a scheduler does, provides a .now method on it, .now property to say when's now, and a scheduling capability to say, run this action at some point in the time, some point in the future, or as soon as you can. How this ties into the RX operators is every operator which is time dependent takes a scheduler as a parameter. Now, a bit of advice if you're using RX, whenever you use any of these operators, delay, buffer, window, even return, if they take a scheduler, always explicitly pass one in. That then allows you to swap that out for some kind of test scheduler at some point. It also makes very explicit how these things are going to be scheduled. If you look on the blogs and do a bit more research in that, you'll see why that's quite important. It also not just abstracts time, but because it's doing scheduling, it also abstracts the location of where the code is going to execute. And in fact, the team are currently doing a whole load of work on allowing you to execute your RX queries in Azure, for example. So what you can do is, if you did this a.delay with a scheduler, this gets a little bit mind-twisty, warning you. If you did a.delay scheduler, and then some code after that, and that scheduler was an Azure scheduler, then what would happen is this code after it would run in Azure. Right. So there's some quite interesting capabilities that will come out of that work. But also you can say, it also allows you to control concurrency as well. You can specify here a scheduler which is a concurrency induced in. Sorry. The scheduler you use can determine what kind of concurrency you're introducing. For example, you can say use the thread pool, which introduces concurrency. You can say use the current thread, which doesn't introduce concurrency. You can say use your own test scheduler, which does whatever you want it to do. So this is a very powerful tool, a very powerful aspect of RX, but I'm not really going to dive into that too much, because that's another level down. I'll take questions on that if you want at the end. Okay.
Okay. We get this. you know, I don't really need one of those, do I?
Oh, come on.
Okay. So, as a crash test dummy, all right. So you know, we use this, and you know, we built a nice little application with it. The things that impress me about it, firstly, the application that we've ended up with is much smaller than a traditional procedural application would be. There is not a lot of code in it, really. Not a lot of lines of code. I mean, lines of code that are there do tend to twist your brain a little bit sometimes, but you know, there's actually very little code to do quite a complex thing. And it's incredibly easy to test because, you know, we can just, you know, put you know, mock event streams into it and control time. It's easy to test. It's also, you know, we can control everything about it. We can be the ability to you know, we're not really, because we can do almost anything with this syntax. We can control in great detail exactly how the code is working. And you know, flexible is, well, it is incredibly flexible. You can add you can add operators you probably shouldn't, as we've discovered, right? You know, you can add an infinite number of operators to confuse future generations. But yeah, you can make it do almost anything you like. And the downside is it's only just new. It's only a few months old. And so there are improvements that will be made to it. The debugging experience needs some improvement. It's, you know, semi-non-existent.
Yeah, but
really.
I think frightening was the word.
Yeah, frightening. I think, yeah, frightening was the word that I used. Yeah, yeah. You know, so it doesn't work. Why? Yeah. All right. Let's start drawing. Actually, you know, that is exactly what we do. Is it doesn't work. Why? Let's go to a really large whiteboard, reduce the number of events, and start drawing marble diagrams to work out what might have happened there. It's a kind of a debugging experience. And also, the trouble is, it's, you know, especially for an old bugger like me, it's a completely different way of thinking about programming. I mean, okay, all right, it's my 7th or 8th completely different way of thinking about programming. So yeah, I shouldn't really complain, should I? Okay, but it's another one, right? You know, we're going to have to train, you know, generations of people to do it. But it's actually well worth it. I mean, to do these particular types of applications, it's like, it's just killer, basically. I mean, that's pretty much. And yeah, what else? Yeah, the stack traces, that's also quite frightening. Yeah, it fell over. Let's have a look at the stack trace. Oh my God, you know. So many virtual method calls. So little actual information, yeah. Okay, and that's pretty much it.
On that front, they are,
Yeah.
the framework's only just been released a couple of months ago. The tooling, the documentation, they're working on. There are tools to help debug this stuff, but it's still in the sort of printf camp. Right? That's the kind of level of debugging in there. Sort of IntelliTrace stuff's coming and so on, but the best way to debug this stuff is the tests, really, is unit tests.
Yeah. As per usual.
Yeah.
Lots of unit tests, good, yeah.
Okay, at the beginning, I promised that I'll give you some guidance as to where this product is, or this tool set's appropriate and where it's not appropriate. I'm actually going to do this interactively. I'm going to ask you why you think this is appropriate or not appropriate, whether this is an appropriate tool for different categories of problem. I've got some more beach balls to give out. So first of all, automatic parallelism. So if we wanted to take some query or some operation and automatically spread it over a whole load of processing, is this the appropriate, or multiple threads, for example, is this the appropriate technology? Have I given you enough information to make that decision? No to the not enough information? Sorry? Even if it's event-driven, the answer is still no. Yep, p-link. Oh, that's 2. Well, 2. I'll give it 2. There. Sorry. Yeah, the reason why is that all concurrency in Rx is explicit. It's not over there. Sorry. It's very much, it's an explicit programming model. So any concurrency, transactions, state persistence, and so on is all you have to manage explicitly yourself. You can, with schedulers, introduce concurrency, but you have to do it yourself. Right? You have to say, I want concurrency. It's not automatic. It's not just here's a query, run it over lots of different threads. P-link is a great example of technology to do that. Okay. Automatic state persistence. Do we think this is an appropriate tool to automatically persist the operations as they're flowing through these queries? Deal with transactions and that kind of stuff. Anyone? No? Why? Sorry?
1 and 2.
Excuse me. Okay, I'll give you that one anyway. Oh, sorry. If you come and grab one afterwards.
You've got to.
As long as your state's small, I guess, between each one of your callbacks, and it's okay if you're trying to maintain a large state.
That's a good point. So the point was, if your state's small as it's going through the callbacks, then it might be appropriate. That sort of thing, yeah. The reason is this is all in process. It's just a virtual method call. It's just there's no magic in here. There's no interception layers and so on. So really, it's not like something like Workflow Foundation where every time it transitions in and out, it goes through a state boundary. Right? It's all really, and this is why it's fast. Rx is fast because it's just virtual method call, each down the chain, really fast. It doesn't have any of those layers. If you want, you can add some of those layers in there by putting in the middle some state persistence in between your operators. But something like Workflow Foundation is much better for doing the automatic side of this. Procedural asynchronous. Okay. Does anyone understand what that, or does anyone actually have an idea of what I mean by that? No. Okay. Good. Or not, yeah. Okay, so. Oh, why not? Come on. There we are. So, by the way, the logo is the RX logo on the balls, for those who want to know. Procedural asynchronous is step, 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 oh, do something, come back when it's finished. Step, 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 oh, go out, do something, come back when it's finished. Step, step. If this, go and do that. If this, go and do that. You know, while loops, for loops, those kind of things. So your standard C# VB.NET code, but just being asynchronous, jumping out somewhere and coming back. Right. So that's what we mean by procedural asynchronous. So any guys' ideas whether this is the appropriate technology if you want to do that kind of programming? Right, okay. So actually, in fact, I'll give you a ball for that anyway. You've mentioned something which I haven't mentioned at all in this talk, just because it's another layer. So yeah, one of the advantages of synchronous programming is try-catch, handling errors, and a call stack. This gets really tricky when you're doing asynchronous programming. What Rx does is the iObservable interface has two things. It has onNext, sorry, it's had three things. It has onNext, onCompleted, and onError. So any observable can say either here's the next item, here's the next item, and then may terminate with either an onCompleted or an onError. There's a whole lot of guarantees around, like the fact that onNext is serialized, and that once you receive an onError or an onCompleted, that's it. Observable is not allowed to send you any more items. And that strict grammar of observables is actually very powerful and enables a lot of these scenarios. But the onError channel, as it were, the onError messaging, sort of propagates through your link query and comes out the end. And that's how you can get your error messages flowing out. And that's actually one of the nicest parts of Rx. And I haven't told you about it because I think it's another layer of complexity. But one of the nicest parts of Rx is the fact that you build this whole chain of operators, and you know that wherever you subscribe to this, in the end, that if an error occurs anywhere in this whole mass, it will effectively bubble, the same way that bubbling up of a call stack, right, in a synchronous application, will bubble through the operators to where you subscribed. And the thing will terminate in the same way that the programming model and the synchronous model also terminates when you get a call, an exception thrown all the way up. So from that perspective, and that's kind of one of the key points, but it adds that extra layer of complexity, which is why I didn't talk about it before. But whoever said no, I think it's a general murmur of no, so procedural asynchronous is correct. If you want to do if statements and do different bits of code dependent on the results of something else, and want to do strict sequential loops, and you want to be very state-driven with your method state or your member state, and the await keyword, for example, is a good way of doing that in the next version of C#. However,
The key, I've got it.
yeah. If you want to do declarative asynchronous, which means posing up constructions. So a case where you'd want to do this, going to a search engine, getting the list of results from the search engine. For each of those items, you're then going to go off and do an asynchronous call to, say, the top 10 of them. Asynchronous call, go and get the web pages and do some processing on those. That sort of thing works fantastically in Rx, because you can just do a couple of from statements, and you get that kind of multiplying out. In fact, whenever you're going to get a set of events, for each of those events, you're going to do another set of stuff. Then you're going to compute some information, and then collapse it down into a result stream at the end. That's quite abstract. That's where declarative programming is fantastic for doing that kind of thing. Whereas the multiplicity is what gets you with your procedural asynchronous programming.
Couldn't you just take that whole bunch of procedural stuff that you were going to do with it, make a new operator out of it, or a new
Okay.
particular chain?
Yeah, thanks for that. That's how most people start using Rx. And you do exactly that. You go, oh, this Rx stuff, that's not how it should work. It's not right. I know how it should work. I'm used to it doing this, and so I do this, and I can't find the operator that does exactly what I want. So what I'm going to do is I'm going to go and I'm going to rewrite an operator which does exactly what I want. And you do that, and you get sort of about a couple months into the project. You've got all these extension methods. And then you find that you're not actually obeying the grammar in your operators, or that you haven't got you're dealing with merging concurrency correctly, or doing all this stuff. And you end up ripping out half that code, and then rewriting your code in about half the number of lines. But to get to that point, it takes you 3 months. And that's why I said at the beginning, is it worth your time getting your head around this? Because this is hard stuff. This takes a long time to really get your head around how to describe the problem and solve it in this declarative fashion. Once you've done it, great. You can test the whatever out of it. It runs really fast. You can scale it up. You can start slicing your stuff across multiple threads if you want to. Lots of stuff you can do with it once you put it into that declarative form. But getting your head around how to do that, it does take time. The forum's a great place, though. The people on the forum are really helpful. And I'm one of them. OK, so declarative asynchronous, multiple events or sources. If you've got streams of information, different streams coming in, you want to manipulate them together, like price streams and holding streams and kind of stuff. Really good for. Time-dependent behavior. Want to start doing timeouts or buffering or windowing operations. Excellent for. Last one, again, is another sort of side issue I haven't talked about. Query offloading. When I talked about LINQ, I said it was a language over the top of providers. The same way that LINQ's got linked to objects and linked to SQL. With linked to SQL, it takes the language of your query, transforms it into a SQL statement, and runs it. With Rx, you can build, or other people and vendors will be building, Rx providers that take your Rx query, transforms that into their native engine, and generates real-time queries in whatever their language happens to be. So take your favorite service bus, an Rx strongly typed query using LINQ, Then that gets transformed into your service bus publisher's query language. So this, I think, in some ways is going to become the most important part of it. But this is still very, very young. Right. So that's why I left it there. Okay. I think, Chris, do you want us to go to the...
Yep, sorry. Except first, here's the times for your sessions tomorrow.
Oh. Okay.
1 and
If
2.
people are interested in seeing some hands-on work with RX, with actual coding, I'm going to do 2 sessions tomorrow at the Microsoft Create booth in the Community Center in the Expo. One at 1 p.m., Reactive Overview, and at 2 p.m., Reactive Deep Dive. So if people are interested, come on to that. I'll be there.
Right.
So I guess any questions? We've got about 3 minutes or so.
Does it run on Xbox? No.
Actually, it runs, sorry, you're right. It actually runs on Windows Phone, runs on, runs in JavaScript, runs in .NET, various ones, even runs in Mono, well, it's not supported. So, runs in a few places. Yep.
So that raises the question of
Please fill out evals, please, if you like the show, if you like the session.
when it's actually running, is it generating garbage? You had RX.